Okay, let's dive right into this. Welcome to this explainer. Now, did you know that 99% of all international data travels through hair-thin glass tubes sitting at the very bottom of the ocean? It's wild to think about. Today, we're going to embark on a really fascinating journey to demystify the incredible physical and economic forces that dictate exactly how all that data travels across the globe. We often think of the internet as this invisible, weightless cloud, but the reality is deeply, deeply rooted in physical infrastructure, mathematical limitations, and just some absolutely brilliant engineering. So today, we're going to unpack the true story of how we've systematically conquered the laws of physics to bring multi-gigabit connectivity to the modern world.
So here's our roadmap for today. First, we'll tackle the copper bottleneck. Then, hacking the shared medium. 3, the optical fiber revolution. 4, bridging the digital divide. And finally, number 5, global standards in space. Let's get moving.
Before we get into the heavy technical details, I want to ask you a pretty fundamental question. How does the internet actually reach you? Right now, as you're taking in this information, I want you to really think about the physical reality of what makes this possible. We're talking about invisible electromagnetic waves bouncing through the air and these hair-thin underground glass threads stretching across entire oceans and continents. It is an absolute modern marvel. And the craziest part? It all started with a network that was never ever intended for data in the first place.
Part 1, the copper bottleneck. Fighting legacy wires.
For decades, our foundational telecommunications topology, basically the phone network, was built purely for the human voice. Engineers restricted it to this tiny 300 to 3400 Hz frequency pipe, which was deliberately filtered just to keep out background noise. And well, that brings us to the Shannon-Hartley theorem. Now, you don't need to be a mathematician to grasp why this equation was an early engineer's absolute worst nightmare. It dictates the fundamental ground rules of physics. To push more digital data through a channel, you either need to increase the bandwidth, meaning you need a bigger pipe, or you have to dramatically improve the signal-to-noise ratio. So engineers were basically trapped. They were trying to force massive amounts of digital data through an analog, highly restricted copper wire that was inherently noisy.
Let's move to NEC and see how this built, because to get past those physics, engineers essentially had to hack this copper medium. Back in the 90s, dial-up maxed out around 56 kilobits per second. To get faster than that, they shifted to DSL technologies, expanding the frequencies way beyond the human voice. But there's a catch. Higher frequencies mean the signal dies out a lot faster over long distances. Notice the chronological trend here? Engineers squeezed out more and more speed, eventually hitting a whopping 1 gigabit per second by systematically shrinking the length of the copper wires. They even invented this thing called vectoring. It basically acts like noise-canceling headphones, but for copper lines, actively blocking out interference to keep those speeds high.
Moving on to part 2, hacking the shared medium, the cable revolution.
While the telephone companies were busy fighting copper limits, cable networks faced a completely different physical challenge. They were originally built as a one-way street, right? Just meant to broadcast television from a central point down to your house. To turn that one-way TV system into a two-way digital highway, man, the engineering was staggering. First, they had to rip out all these noisy analog amplifiers and push fiber optics deep into neighborhoods. Then, using DOCSIS standards, they introduced a brilliant technology called OFDM. In simple terms, OFDM allows the network to dynamically dodge what's known as noise funneling. That's basically when a single bad wire or a loose connector in your neighbor's house sends a bunch of interference echoing back up the shared line. Navigating around that interference is exactly how they managed to squeeze up to 10 gigabits of capacity out of noisy, shared coaxial cables.
Which brings us to part 3, the optical fiber revolution, total internal reflection.
Eventually, as amazing as those copper and coaxial hacks were, we just hit a physical wall. The solution? Replacing the messy rules of metallic electromagnetism with something far more elegant. The speed of light, bouncing through pure silica glass using total internal reflection. And this brilliantly illustrates a massive paradigm shift in how we use the internet. For decades, those older copper and coax networks were deliberately asymmetric. High download speeds, sure, but painfully slow upload speeds. And that made total sense for a consumer internet, where we were mostly just downloading web pages or streaming movies. But modern fiber optics introduced true symmetric connectivity, equal upload and download speeds. This is tailor-made for the creator internet we live in today, where remote workers need real-time virtual workspaces, businesses are doing massive cloud uploads, and global teams are collaborating seamlessly.
Just look at the staggering jump in capability when we upgrade to modern optical fiber.
By using XGS-PON, which is a standard running on a single, incredibly pure strand of glass known as single-mode fiber, we aren't just hitting nearly 10 gigabits per second symmetrically. Check out the distance limit, 20 kilometers or more with virtually zero signal attenuation. Fiber absolutely obliterates the physical distance limits that crippled those older copper and coaxial networks.
So why does all this physics matter to your everyday life? Well, these symmetrical speeds and virtually zero latency fiber links are the absolute foundation for advanced modern applications. We are talking about Industry 4.0, where automated factory robotics need less than 5 milliseconds of delay just to operate safely. Or telehealth, where doctors can instantly transfer massive diagnostic imaging files to save a stroke patient. We're even seeing robotic telesurgery globally, which is truly incredible when you think about it. I mean, a surgeon operating on a patient continents away requires virtually zero packet loss. And on a broader scale, it creates macroeconomic resilience by completely decoupling human capital from physical geography. You can literally live in a rural remote town and work seamlessly for a global tech firm.
Part 4. Bridging the digital divide. The geographic chasm.
But despite all these engineering marvels, we are facing a really harsh reality, a profound gap between urban and rural access known as the digital divide. And the stakes here are incredibly high. Economists have proven that for every 10% increase in broadband penetration in a developed economy, there is a corresponding 1.2% to 1.38% increase in gross domestic product. So connectivity isn't just a convenience anymore. It is a massive economic multiplier. It reduces transaction friction and integrates otherwise isolated markets right into the global supply chain.
But bridging this divide means we have to fight some absolutely brutal math. In urban environments, deploying fiber has a really high upfront capital cost, but it's quickly offset because you literally have thousands of subscribers per square kilometer. The business case is highly viable. However, in rural distance deployments, the math completely breaks down. Actually, scratch that. It doesn't just break down, it evaporates. Trenching fiber can cost anywhere from $20,000 to $80,000 per single mile. If you only have, say, 5 houses on that mile of road, the math is just mathematically prohibitive without heavy government subsidies. This geographic penalty starves remote communities of human capital and severely erodes their local tax bases.
Finally, Part 5. Global Standards and Space, the Final Frontier.
So the crucial point is this. If we can't afford to trench glass fiber to every remote cabin on Earth, how do we solve this rural economic chasm? Well, the answer lies in an invisible web of global coordination and space. Think of it like a massive governing pyramid. At the top, we have the ITU handling global, treaty-level spectrum so satellites don't crash into each other's signals. Below that, regional regulators like the FCC and ETSI managing local rules like opening up the 6 GHz band for your home Wi-Fi. And then engineering bodies like IEEE and 3GPP writing the actual protocols for Ethernet, Wi-Fi, and 5G. Without this precise, incredibly complex harmonization, our global internet would instantly shatter into a mess of incompatible regional silos.
And thanks to those standards, we are now deploying the ultimate solution to the rural divide: low Earth orbit mega constellations. Now, legacy geostationary satellites orbit way out at 35,000 kilometers. That sheer physical distance creates a massive latency bottleneck. It physically takes half a second for a signal to go to space and back, making things like real-time video calls a frustrating, laggy mess. But modern LEO constellations orbit incredibly close to the Earth, between just 500 and 1,200 kilometers. This drops the latency down to a mere 25 to 40 milliseconds. This effectively bypasses the limits of legacy satellites and actually rivals terrestrial fiber, finally bringing viable, high-speed broadband to the absolute most remote corners of the globe.
It's really worth taking a step back here to realize that broadband is no longer just a telecommunications service. It has achieved the status of a general-purpose technology. Think about what that really means for us. Just like the introduction of electrification or the steam engine back in the day, modern broadband is the true underlying invisible substrate of modern society. It is the core catalyst that spawns absolutely everything else: cloud computing, the Internet of Things, and artificial intelligence.
We've traced this incredible engineering journey today, from screeching dial-up modems hacking legacy copper wires to lasers pulsing through pure glass, and now to thousands of satellites beaming data down from low Earth orbit. So I want to leave you with this provocative thought. What happens to the global economy, to human innovation, and to society itself when every single square meter of the Earth is finally blanketed in symmetrical, zero-latency connectivity? What happens when the limits of physical distance and the laws of physics are finally fully conquered? It is an absolutely incredible future to imagine, and the best part, it's being built right over our heads and right under our feet as we speak.